Now we have Martin Zbudila, who will be talking about Mosaic. It's a privacy-preserving analytics platform for IoT data using MPC. So welcome, Martin.
Okay. So hello everyone. I'm Martin, and I will present Mosaic, which is a privacy-preserving data analytics platform using MPC. And it is a joint effort by researchers from COSIC K11 and University of Ghent in Belgium. And so what is Mosaic? So Mosaic was a project funded by Flemish government, and what we designed was this data analytics platform. The output was a proof of concept implementation of such platform. And we instantiated it on a concrete use case, which is machine learning-based heartbeat analytics. And so in this talk, I will try to go through the goals of this platform and describe how it kind of works. So we have 4 main components there, which is an IoT device, so a low computation device, which is a source of data. Then we have Obelisk, so this is just a central database that stores encrypted data. Then we have MPC servers that perform the computation, and a web application, which is a user interface through which the user controls what happens with his data. And so, what are the goals of our platform? So on the right, you can see the basic architecture of our platform as I previously described. So we have the IoT sensor, then a central database, the 3 MPC parties, and web browser where the user has the interface. And so our goals are end-to-end data confidentiality, so the data remains encrypted throughout the whole life cycle, from the moment it leaves the IoT sensor until it's decrypted by the user on the web browser. Then we want the user to be in full control of his data, meaning that only a particular user can access his encrypted data on the database. And also the user chooses when is his data computed on and by what parties. For correctness, what we mean is that we assume the computation achieves the same, is correct as if it in MPC, as if it was done in plain text. We also want our platform to be scalable to accommodate multiple sensors and multiple users. We want it to be interoperable, meaning that we don't want it to be bound to a specific use case of the machine learning heartbeat inference, but if you have any other use case, you can just plug in your data, your function, and instantiate it. And of course, we tolerate some adversaries, which brings me to the threat model. So the adversary's goal is to undermine data privacy, data control and correctness of the computation for other users. We assume two types of adversaries. First one is a malicious adversary, which can control up to n-1 users. It can also control the central database and up to one MPC party. We also assume a semi-honest machine learning model provider. In this talk, I will not talk about the model provider. We already assume that the machine learning model is pre-shared on the MPC parties. Okay, so what MPC engines we use? So the first one is the engine for machine learning inference. This is implemented in MPSpeed. It uses a free-party replicated secret sharing with malicious security. This is a protocol in MPSpeed noted as malicious rep ring party, malicious replicated ring, if you are familiar with it. So it's based on the initial construction of hierarchy for replicated secret sharing, and it's done over rings of integers power 2 to the 64. In our protocols, both offline phase and online phase are executed on the fly. And so we wanted to minimize the total computation time. And so we replaced the original truncation in this replicated secret sharing by master truncation, which doesn't have any offline phase. So it's a probabilistic truncation, but it saves us a lot of time. We use fixed point arithmetics with 8-bit precision, 16-bit input length, and we achieve the same accuracy with these parameters as plain text on the heartbeat data model that we have. Now the second engine is for distributed encryption and decryption. This is implemented in Maestro framework. This is again free-party replicated secret sharing with malicious security, but this time over binary field extension. And so you might notice that we have two different protocols in arithmetic and Boolean domain, and we switch between these using the standard approach proposed by ABY3, which uses ripple carry adder circuits. So these are just binary circuits that are computed to switch between these domains. Now let me briefly talk through the use case. So as I mentioned, it's about heartbeat analytics. So we assume that the user has some smartwatch that collects or measures his heartbeat, and at some point the user wants to securely know whether he has some arrhythmia or not. And so this data set is taken from Kaggle. The model that we compute is also taken from Kaggle, so it's a very simple 5-layer dense neural network, followed by ReLU activation functions. In the last layer, it's softmax. And on the right, you can see the data. So it's we distinguish between 5 classes. The first one is normal heartbeat. All the others are arrhythmia. These are standardized classes in the medical field. And each sample corresponds to a single heartbeat. It's roughly 200 features long, and it's taken from a 10-second window. And what is important to note is that apparently it is enough to look at one heartbeat during a 10-second window in order to classify arrhythmia. And so this was very important when designing our platform, because our goal was then to accommodate many users, knowing that every user has to have a result of his heartbeat within 10 seconds maximum. And so then we have two different processing modes. The first one is ad hoc analysis. So again, we have this IoT sensor, and every 10 seconds it sends one heartbeat sample to the Mosaic platform. So this sample is symmetrically encrypted, so it's just a standard AES encryption using user secret key, and the ciphertexts are stored in this Mosaic platform. Now, for the concrete use case, imagine that the user has a smartwatch which is collecting this heartbeat data, and at the end of the day he will say, okay, around 3 p.m. I was feeling bad, and around 7 p.m. I was feeling bad, so I will just pick the time frame where I was feeling bad, and I want to analyze the samples. And so in the evening, the user comes, he picks the samples, and then requests analysis on this. Now the other case is a streaming case. So in this case, the user would go running, let's imagine, and so he wants continuous analysis of his samples because maybe he has diagnosed arrhythmia and he wants to know that the moment the arrhythmia starts, he has to stop running. And so he enables this streaming mode from his smartwatch, and so the data, the moment the smartwatch gets the data, it's immediately sent to the Mosaic platform, immediately to processing, and back to the user to display on the smartwatch whether the heartbeat is okay or not. And so let me go through how does this all actually work. So this is a very scary slide, but let's focus on the left side. So we have this IoT sensor, which has this heartbeat data. Every sample is symmetrically encrypted using the user secret key, as I mentioned, and this is stored in the central database, which is called Obelisk. Now the user can come, let's say in the evening, as I mentioned, through this web browser. He can log in, put some password. This password is his secret key, and request analysis. Now, the moment the user requests analysis, the secret key is secret shared on his browser, and each secret key, each secret share of the secret key is encrypted with the public key of the corresponding MPC party. This is then sent to the MPC parties, and now MPC parties perform distributed decryption of the ciphertext of the data. Then they compute machine learning inference, then distributed encryption again to obtain the ciphertext of the output, and this is again stored in the central database. And so now the central database has the ciphertext of the machine learning output, and then the user can again log into the dashboard, see the output, and decrypt the output with his secret key. Regarding some results, so as I mentioned, we had 3 servers. They were not so powerful servers, so which with 4 cores, 16 gigabytes of RAM, but we had a very good network between them, so 9 gigabit network. And so first, some results for the ad hoc analysis. So these numbers are measured from the moment user requests analysis to the moment the user sees it in his web dashboard. And so you can see for a single sample, the whole process takes roughly 1 second. Then if you move to larger batches, the amortized cost per sample is lower. So let's say for 128 samples, it takes roughly 6 seconds. Now for the streaming case, so what we measured is each user has 1 IoT sensor, and how many users can we accommodate? So the data streams column means number of users we can accommodate, such that every user has this result within 10 seconds. So consider if we only compute batch sizes of 1, every single sample will take roughly 1.1 seconds to get back. And so if we want every user to have the result within 10 seconds back, we of course can only accommodate up to 9 users, because 9 times 1.1 is 9.9 roughly, which is still within 10 seconds. Now, we also measured larger batch sizes. So for example, let's take the 64 batch size. Now, of course, if you are a first user, your heartbeat sample is added to the queue, and you have to wait for 63 more in order for the batch size to get computed on. And then your batch size is computed, and then you get the result. And that's why we distinguish between maximum and minimum latency, because if you are first in the queue, then you wait much longer, as if you are the last one, the 64th batch, then your sample gets computed immediately on. Yes, and based on our evaluation, we can roughly, to accommodate the 10-second window, we can roughly accommodate about 140 users for the streaming case. Now, I do have a little demo, which just doesn't show much, but if I can play it. So this shows the dashboard. On the right, you can see what the user sees. So this is his data collected throughout the day. Here it's every second. And so in the evening, let's say the user comes and collects these 4 samples because he wants these 4 samples to be computed on. Then the user also has a control over which MPC parties he wants it to compute on. So in practice, we imagine that this could be a bunch of servers from Google, Amazon, other companies, and yeah, the user can pick which 3 he trusts. In our proof of concept implementation, we only had 3. So yeah, the user picks these parties, and then he picks the analysis type. So as I mentioned, we don't want to be bound to the heartbeat analysis. It can be any other application that we have. This just says the MPC parties, which binary to call. And the moment this analysis is queued, the user has to enable it or send it to the party. So he picked 4 samples. So he chooses a batch size of 4, and then he can queue batch. So this will send it to the MPC parties, and you can see on the left all the MPC parties got a HTTP post request, meaning that they got the data and they are now computing on it. Okay. The user immediately went to the batches, and this is very quick. So it's only a batch size of 4. So this computation took roughly 1 second, I believe, and he can already see the status, which is completed. And now he can view the result. And yes, so he got the result from each MPC party, and from each MPC party he got exactly 4 results. And the result is a confidence vector for each sample. As I mentioned, there are 5 classes, so confidence for each class. And yeah, that is it. Okay, some lessons learned from this academic collaboration is that MPC researchers are not software developers, so maybe some are, but most of us struggled with with understanding each other. For example, for the HTTP documentation, so we set some names that okay, we will use this. But then the guy from Ghent, who was in charge of the central database, told us that oh look, you can't send this in post request, or you can't do this in get request. So he completely changed the way we communicated, and this took a lot of time to change back. So there was a lot of miscommunication. And yeah, even though we agreed on a lot of stuff, documentation takes a lot of time, but it is very important to do. So we trusted ourselves. We know what are we doing as the MPC guys. But then when debugging came into the way, we realized that okay, we should have spent much more time documenting literally everything, so that the guys on the other side can actually understand our code. Next one is that batching is not equal to batching, depending on which area you come. So for us MPC researchers, it means simple vectorization. But in the database context, they were always talking about concatenation, which we only realized about after a month of communication, of meetings. And then when I expected 4 samples, I got one ciphertext. I was in the MPC party. I was I was confused. Why am I getting only one? So yeah, just some words can mean different things in different fields. And then last one is that okay, we know kind of that MPC is secure up to the library if we trust the implementation. But what about the rest? Okay, so we know symmetric key encryption is secure. But one thing that happened is that after the computation was done on the 3 servers, so each server has the ciphertext of the output, and each server on the MPC side sends these results to the central database. But what the guys on the database did, that they just accepted only one result and they displayed it. Now, of course, this is an issue because we assume that one of these parties can be malicious. And so you really need to accept all 3 of these results and check that the ciphertexts are equal. And then, yeah, if they are not, then clearly there was some malicious behavior. And this we realized actually about a year after the project was done, that this was implemented this way. So, yeah. And some takeaways. So what we presented is what we done is a proof of concept implementation based on replicated secret sharing with malicious security, and hopefully we have shown that machine learning can be somewhat practical for MPC can be somewhat practical for machine learning tasks. So thank you.
Thank you. That was a very cool talk. My main question, first of all, was like in the streaming case, like doing it every 10 seconds. That sounds like extreme to me. Was it maybe considered that you do something on the IoT device, or that you pretty much use a really weak model that is like an approximation of the good one that has like a low false negative probability, and then you filter out samples so you only send those which might possibly be a case to the servers for computation? Or
yeah, we have never looked at it. So our point was that the user, it's not only a processing platform, but also a storage. So you just don't want to do anything on the IoT at all. You want to really make sure that everything is stored on the data. Also, we got the question in another talk, like why do we encrypt on the MPC servers and store the encrypted way? Why don't we send the shares directly to the user? Simply because we want it to be centrally stored in some point. And so, yeah, we've never considered anything to do on the IoT side or the user or the database, in fact.
okay, and one other question. You mentioned this case of like the faulty corrupted MPC server sending back a false ciphertext. How did you handle this case? Did you like do a majority vote of the servers that like you took the majority ciphertext, or?
No, so we just compare, and if they are not equal, then we just flag it and like say the whole computation was wrong.
Okay.
Yeah.
But you could, if in the case of like a fault tolerant MPC protocol, you could do something like to still use the result, right?
Yes.
Okay, thank you.
Thanks very much for the very practical talk in the theoretical MPC section. I appreciate that a lot. I have a question about channel deployment of MPC style applications with web servers. Like your trust model assumed that the web server can be corrupted as well. And I see that in many cases. Like, it's a challenge. How do you make sure that if you have a corrupted web server, the end-facing user sees a correct website? Or do you need some browser plugins with certificates? How do you make sure that the website is not compromised, or the web dashboard that you have that just leaks the user's inputs unencrypted somewhere?
So this we actually don't do. So the malicious emoji or whatever I had here was to denote the user himself is not malicious, not the web browser. But indeed, this is a difficult task. So we don't do that. We trust that the web server on the user side does actually what it needs to do. But this comes then deeper. Like if the user doesn't trust the website, what it does, then he can also say, okay, how do I know that yeah, the MPC parties really execute the code and etc. Right?
Well, the MPC parties, this is some compiled binary, right? We have good control over that, or this is a closed system, kind of, the MPC parties. But the user-facing thing, maybe we find a solution over the day. It's a running theme, right? How could we tolerate trusted, not trusted web servers to ship our MPC applications to end users, which I think is quite challenging.
Yeah, yeah.
Thanks very much.
Do we have more questions?
Yeah, thank you for the talk. I was just wondering, in the real use case, like who do you envision the parties who are running the MPC servers, right? Because like for a lot of IoT devices, it would be a single provider, like it would be like multiple servers, but controlled by a single user, right? So what do you envision, like in practical, for this approach?
Honestly, we just envisioned one server from Amazon, one server from Azure, one server from Google, and then we also assume that it's in their interest not to collude with each other, because yeah, we can then always have a look at the logs and verify whether they are doing they are doing the protocol correctly. Yeah, that's I guess my answer.
Yeah, thank you.
Just to follow up on your last answer, did you actually implement it with one server from Amazon, one server from AWS? Because I understand that that's actually currently a challenge.
Yeah, these are just servers at the university.
Any more? No. And probably it's more about who controls these servers. I mean, Google, Amazon, and AWS most likely won't run it for you or for us. It's more about who has admin rights to control these cloud nodes. And that's something which we have to answer. And we keep on landing on that questions very now and often. Right, no, so thank you very much, Martin, for a very well-balanced talk. That ends our first session.